Now he has a very successful practice, and I'm going to leave you with Arthur.
Thank you very, very much, Cindy and Federico. I still remember being an intern at Zaha and Federico kind of hitting me with the newspaper because I was late or something. That's my memory of it. And thank you, Johannes, very inspired by your recommendation. So this is a bit of a lecture. I might as well go for it. Same, I want to throw lots of information and see if there's anything that inspires you and if you want to keep it. And also just to tell you the journey of someone who learns, or he was, I in a way was sitting in your seat maybe 10 years ago when I first did the visiting school at the AA, the very, very first one. And so I hope you'll be inspired and see that this knowledge will open up opportunities. And like Federico said, the AA is beyond normal architecture, so this is kind of why I'm here, and I hope it will show in this talk. This is a sort of ecosystem. I wouldn't say that I'm just an architect. Of course, it's opened up things for me. I can see also for Johannes, he's done many, many different things that are not necessarily what one would call architecture. So we are asking you to be open-minded about what architecture is. I teach at the University of Westminste. This is the blog I kind of publish all the research. I'm also simply Rhino official Grasshopper teacher since 6 years now. This is my business. And I also have a fabrication laboratory. You'll see things happening like this a lot with people that do parametric design, is that fabrication is crucial to what we do, so we end up having fab labs on the side. And also developing software. Silkworm is a open source 3D printing plugin for Grasshopper that generates G-code for you. And so all these are things I've been working on with some friends and collaborators. A lot of the projects I work on are smaller scale, but they're not just design, they're design and making, and clients are just about getting used to the idea that we can also be contractors. I know Johannes said he didn't want to be one, but we end up having to be one because the kind of stuff that we design in the office is just too hard for any contractor to fully understand. And when you start using those tools, you'll always end up thinking, well, actually, what if I just did it because it'll be easier? So these are a couple of the projects that I worked on. I'll mention them, so I won't dwell too much on it. I've been taking my students to a festival called Burning Man in the USA to build structures with them, which was the ultimate architectural bootcamp. And I hope this one will be easy in comparison. But what I'd like to show you is what sort of architecture can emerge from parametric processes. So forget about the kind of technicalities a little bit and think that the beauty about those tools is that you can bring many, many, many different things together. Grasshopper is an ecosystem. It's not necessarily one tool, but many, many tools. I see here, it's classified by downloads, so we're a little bit behind. So this is the things you can download from Food for Rhino. It's a online marketplace of, not really marketplace because everything is free because it's done by hobbyists and people like me that enjoy this process and have taken so much from the community that we're often giving back. So all these designs are made with Fab Labs. I think Pablo discussed the opening up of Fab Labs around South America. In London we have, in East London, a place called Makermouth, which is within Hackney Road and so on, which has many, many, many Fab Labs. And people end up going there when they have things they want to make. This is forums. Forums, I don't know why it's showing this way, but this is where I started self-learning. Grasshopper3d.com. Don't see this as maybe the end of your learning curve. On the contrary, you'll end up going on the forums. I've learned through asking questions. I've annoyed plenty of people, but then I ended up becoming friends with them. So don't be scared of asking questions and spreading ideas. The more ideas you spread, the more you'll learn and the more you'll be inspired in return. So this is what we set up in London. People book, they book the machines online per hour, and so we end up having people using our machines next to us all the time. The entrepreneurial aspect of architecture is also something I'd like to speak about. All these projects are now, a lot of them are sort of self-funded. We end up doing crowdfunding campaigns on Kickstarter. This is Kickstarter, I don't know if you heard of it. It's crowdfunding. Allows other people to chip in your projects and your initiatives. You don't have to wait for a client. You don't have to be kind of bitter and unemployed, as I was told architecture would be for me. So I'd like to take back a bit of a step into my journey. This is my diploma. My teachers were Franklin Lee, and which Pablo mentioned in his lecture, Brazilian. So I will kind of not spend too much time, but this is a building by Oscar Niemeyer in Paris, my favorite building. And this is a software called Generative Component. The ancestor, the father of Grasshopper. At the time, we didn't have Grasshopper. And we had this. So this was a little graph of the operations. You weren't designing from this. You were designing from these information that you would kind of take and list into a list of operations. The graph would appear. This is a little component that would react to the sun. You have sun rays that are influencing that component, and you could test it live and see the output of the solar ray bouncing against the surface. So by introducing the sun into the model, I could calibrate a component in order to let it output the kind of light that is specific to art or to the kind of activities happening in the building. These are information you get from software such as Ecotect or now Ladybug, Honeybee that you have for free on Grasshopper. They allow you to understand the climate that you're dealing with and therefore do an architecture that responds to that climate. So whether it's the sun or the wind, you're able to calibrate your architecture to exactly what you want and therefore simulate. So here is the sun rays. This is called radiance. It's a tool that you can use to simulate light. And the basic idea was to let light in when it's cold and block it when it's hot, or diffuse it when it's hot, and therefore create a building that would have a skin that knows when the sun will be showing up and when it will be too hot, and so on and so forth. So that was the kind of idea behind this project. At the time, we didn't have giant 3D printers, so I did a small model, but now obviously I would take one of those components and build it large scale. So then I graduated and joined an office that won a competition for a kind of biodome. This is a biodome, but had probably were a bit scared because they won it, but they didn't realize how to make it happen. And the reason I say this is 200 meters. This dome is for gorillas and chimpanzees, and it's in Manchester, so it's not really friendly in terms of climate. And that dome needed as little structure as possible. So structure is another aspect of parametric design. We just covered the environmental aspect. This is called a geodesic curve. So whenever you have a NURBS surface, NURBS, we'll see it in our applied workshops, but there are surfaces that you can calculate the shortest path between 2 points on, and by doing so, you're creating grids that are extremely efficient. And that's because the forces are taking the shortest path they can on that surface. So this is a quick demonstration of how calculating such curves can allow you to get cells that grow with the surface. So by doing so, you get these little triangles, and by getting those triangles, you can then calculate the area that you need for the plastic, in this case ETFE panels, that would provide a kind of very light structure of 200 millimeter deep for a 200 meter span, which is pretty good. So this is a facade I worked on this office. I worked with them on you probably saw this previously. You feed in an image, it outputs the location of where you need to dig a hole. With the kind of tools, so we weren't using a robot, but a sort of pressing machine that punch presses holes, and you feed him radius. The less radius you use, the cheaper it is to use the machine. The minimum amount of radius we used was 3, but the engineer on his side, so you have on one side the fabricator, on the other side you have the engineers that says we need 40% opening ratio onto those panels. So on one side you have information from fabricators, on the other side you have information from mechanical engineers. And so you have to bring all these people together, and Johannes showed it brilliantly, which is now architects they're kind of the orchestrator of many different fields, whether it's engineering or fabrications, and so therefore you end up doing things that you didn't think you were capable of doing, and so the fabricators saw this and wanted to buy that little interface, didn't realize it was a grasshopper operation, very easy, again, like you say, could be done in a day, but that intelligence is not something fabricators are necessarily used to, because they're given tools that can only perform certain things. And so that knowledge really opens up worlds of opportunity in the world of making and architecture. This is a flat we worked on, and these are very early projects. I'm talking just a year after graduating, using a kind of Islamic pattern that would react to the views of people going up the staircase. So when I graduated at the AA, I was told, well, Arthur, this has been done thousands of years ago, the golden age of Islam. They didn't need grasshopper, all these things. So I was like, oh, that's interesting. Okay, so I'll look into it. So this is how you link, so you have points in space, you link them. It's called topology, the way you link things together. And then by changing some parameters, you get from one pattern to the next. And so you can create really interesting transitions, interesting changes in thicknesses, and so on. You can subdivide them, using something like Catmull-Clark subdivision, and so on. And so very quickly you can experiment with perforations and how this could create soft boundaries between your spaces. So these are some early kind of work that I want to show you. And then this is a 3D printing. So this is my first kind of experience. This was for the V&A gallery in London with Guan Li. And it was a kind of 3-dimensional version of that screen that I showed you. And Guan is also a teacher at the Bartlett, came to see me and say, I want to do a cloud. We can only use this kind of plaster-based or gypsum-based printers, which he just bought. And so I looked into clouds with him and looked at different ways to represent clouds. Clouds, if you look at them, I look at clouds all the time. They're little particles of dust that are surrounded by water. And therefore they scatter the light. So scattering means that light comes in and bounces inside billions, trillions of time. And then so it's really hard to see the edge of a cloud. In fact, you can't really see it because there is no real edge. So this is called a purlin noise. Whenever we'll start our applied grasshopper workshops, you'll see that you can take a mesh, a ball, you can manipulate the vertices, you can recompose a mesh, and you can apply all kinds of maps to it. So this is called a purlin noise. It's done by an Academy Award-winning mathematician that developed this for the movies that you might see, 3-dimensional movies. And they were done to reproduce landscapes. So here we're inflating these little cloudlets that are supposed to catch the light. So they catch the light inside its layers. And because they're inflated, they're very resistant to compressive forces. So, and also we've made them slightly thicker at where the folds are. So this is, you have that printer upstairs, I checked. I'll probably take you upstairs as well to show you the different tools. But what this allowed to do is a kind of very solid, it looks more like mushrooms than clouds, but it worked quite nicely in terms of the pattern it created and so on. So, but it was very expensive. So when you buy a printer, a powder printer, you buy the amount of powder And so it's per cubic centimeter, and that's because the people that sell you those machines, they also sell you the powder. And so you end up spending fortunes. I wanted to do the same thing with the cheapest material possible, so that I could reproduce what's beautiful about the project, which is the way it acts with light, but forget about the 3D printing part. So this is called Kangaroo. You will look at it together. This was a commission from the RIBA, the Royal Institute of British Architects, to create a 30 meters long window display in Regent Street next to the Mac store. And this is using a fabric that is this one here. It's called spacer fabric. It's very, very common, and what it does, so here what I'm doing is trying to simulate the behavior of that fabric in order to create a kind of solid sponge that would absorb the light and diffuse it. So it would blur the edge between what's the green area, what's the white area, and you get this sort of magical effect by varying the distance between the patterns. So this is called a smoking pattern. Smoking pattern, you have it in your fabric. It's a very ancient, I think it's British. What it is just information of one in, one out, and so on. But by changing the distance between these patterns, you get more or less resistance. And so therefore you can get kind of really interesting geometries that were very natural looking. And so that's why we probably called it the Magic Garden, because it kind of framed these mannequins in different ways. So this kind of window display was a really great way to show that what we learned from the clouds then went into 3D printing, then went into a much more manual process, also controlled by the computer, but much cheaper. In fact, it happened. So if it happened, the client was happy and even gave us a little bonus. So yes. So then, for some reason, and I'm taking you through my career, I suppose, there is an engineer that really thought it was interesting and was contacted by Virgin Galactic. Virgin Galactic, they send people to they're trying, they're losing a bit of money now, but I think they wanted to take people into space for tourism, and they need a hotel for the astronauts to stay whilst they were just waiting for their flight. So this is called recursion. Recursion is a state in which you take something, and then in the computer, and then you do something to it. Then you take that same thing that you just changed, and you do something to it as well. So it's a sort of loop that kind of eats its own tail. In many ways, we'll probably look into it so we can grow those bent rods. But here it's growing, it's a vector that is moving and rotating, and it's growing in relation to the sun as well. So what's going on is that it creates a mesh behind it, and the angle of that mesh is also trying to prevent the hot rays to go inside when it's hot, and only go inside and bounce when it's cold. So this is a sort of sweeping version of my diploma project that I showed you before. And so this was for the astronauts having a nice collegial lunch before their flight. This is the second version, so the client was very happy because people could not understand how these fabric were doing these shapes and so on, so they came in the shop. And so it raised the profit of the shop by 30% throughout the duration of that project, which is very interesting with installation. I think Johannes is probably confronting this, which is when you put something interesting somewhere, people go and see and want to touch and want to interact. And so the shop owners are very happy, obviously, because then it brings them in. So this is the winter version. They asked us to do a winter version of the Magic Garden. And this is cutting polypropylene. You have a laser cutter upstairs. You can do origamis with it. It's very simple. You just cut 50% on one side, 50% on the other side. And so you can create really controlled patterns by changing, say, the radius of how much you bend in relation to the density of the pattern and so on. So, so this was an interesting kind of effect. Then, I think that was running. Then this is a curved version of that origami. And so think of this as a as the exact same thing as you just saw. You know, I'm talking as I'm showing, so maybe you might want to follow me and the image. But by bending rotated curves, you're actually creating a kind of pressure on the outside that the inside doesn't have. And so it creates these outer curls. Some call it differential growth because it grows. But actually, if you do it with curved origamis, it's the same principle, which is that the outer side has no other constraint, no other way to kind of shape itself, but to form those curves. And it's a really interesting process because you can actually observe it by just cutting a circle and folding it, and then you get these kind of really interesting shapes. When geometry has nowhere to go, it sometimes forms its own form. This is form finding, and by doing it parametrically, you can organize your form finding process into these type of drawings. This is a little matrix, in that it's got columns and rows, and series of information. That is a very good way to organize your thoughts in your parametric model. So I strongly recommend doing it as we are going to look at things together, how your parameters can adapt, and how you can create things that grow based on these modules. And so that's why I'm showing you this as well, is to show you when you start working in this way, you need to think of your shapes as systems. You know, they're systems, they're not final forms. So here it's a project we did in China. It's a simple origami pattern, but by getting informed by the constraint, the laser that we had access to in China was much smaller than the initial drawings. And so basically the fabrication constraints in China was sort of linked to our parametric model. So these are the files we're sending. Grasshopper just kind of populates everything, and therefore we don't really need to worry too much about the size of the laser in the design process. But we integrate the fact that we might worry about it later as we draw it, right? So this is the kind of parametric, sort of, I would say, a typical parametric process. So that's why I want to show it to you, because it's a different way of thinking design. You're creating little animals with the same DNA. The client understood that. That's why he asked us to do more of this project. And clients are, once they understand it, they're very, very happy because you're creating really interesting stuff for very cheap. This is just plastic and a stapler. And so and then you just have fun because as you're modeling them, you're kind of creating these amazing geometry for very cheap. So I wanted to go back to 3D printing. At the time, there was something called RepRap, invented by a really great inventor in Bath University, Adrian Boyer. And printers were getting very cheap. You know, I bought a kit at 400 pounds, and so I was very happy. But there wasn't really something to connect our parametric process with the printer. So with a friend, Adam Holloway, came and then we started literally in his garage, trying to check how we could output what's called G-code. G-code is so simple. It's this. This is X, Y, Z, and F is feed rate, and then there is an E, which is E value. So X, Y, Z, E, right? X, Y, Z, I don't even need to say what it is. E is extrusion value. All you're telling the computer is how much plastic to push inside, and so that's in millimeter. All that is just what you need to tell the printer at the beginning. It's called the header, then you have a footer, and that's it. So if it's that easy, then why are we printing based on slicing? Why are we modeling clean geometry and bothering with naked edges and so on? Let's just send curves to the computer and let the computer figure out the rest. So that was the principle behind it, and so therefore we started doing all these kind of initial tests with Silkworm. And what was nice is that instead of designing shapes, we're designing the toolpath. So the way the machine generates the movement, which is what Johannes was showing you. So then you can send different kind of extrusion values. This is 100% of the extrusion, and then you suddenly retract by giving a negative extrusion. It leaves a little blob, and by leaving a little blob, you get these really interesting patterns. And then you can go more solid, less solid, You can have connectors that are strong whilst having a more ornamental side. It opens up possibilities. And it was fun. It looks like we don't really need glue, but we did at the end. But because we had the same printer here than the one in China that we sent, there was a really clear testing ground in, at that time, my bedroom, which was my office. And on the other hand, in China, sending those printers. So our prints were the same as their prints, which is a new way of thinking fabrication as well. It's exactly what Johannes said. Send your robot. You don't need to send the final shape. In fact, it's cheaper to send a robot or a printer because they do it by weight. So if I send the entire project, it doesn't make sense. So this is the kind of same. I'm not going to dwell too much. It's very, very simple math. I know it sounds weird to say that, but it's the extrusion is. I'll draw it, later on. I'll draw it. But basically, what you're doing is drawing each line here and saying it's that profile, and basically calculating this area of that profile, and then multiplying by the distance, and that's the E value. So you can, if 3D printing is parametric, then you can tell the computer to accelerate, decelerate whilst it's printing, over extrude, under extrude. There's something fascinating about designing with the machine. So this was that project, and it was you cannot see it's next to my bed here. So literally sleeping with a printer and learning. So something you cannot do with a robot. So if you design with toolpath, then that's the kind of drawing you might end up with, because toolpath is more. It's not as solid as a mesh. So these lines here are printing in midair. This is a Delta Tower printer. You have one upstairs, I checked. So we're doing this now in the office as well. So we're printing the lines on top of each other, trying to reproduce the same effect as clouds. I'm a bit obsessed. It must be all my dream time. But by doing such density, you are capturing lights in ways that is really ethereal and magical. And so therefore, therefore I got a bit obsessed with this. And then this is the kind of light rays as they bounce against the shell and come back and scatter inside themselves. And so, that's me looking at it inside. These towers were really interesting because the leftover of the toolpath created these kind of lines, and then you saw the texture is much more controllable. So when you start designing a toolpath rather than a form, you're much more, let's say, interested in the final outcome and the detailing that the machine will give you. And so I ended up buying a laser as well, which was, as you develop a business, you get luckier in that you can invest in bigger machines and so on. So it's just the toys changing, but this is for Bureau Happel Engineering. It's a practice of engineering that loves wood. They've worked on the most famous grid shells out there, and they asked me to look at their reception area, which is that very long space in the center, and really, literally, what they say to me, we want the same as the Karen Millen, but in wood. So I'm like, well, okay, I don't know if wood can do that, but it's funny. I mean, let's try. That's the thing. When I say let's try, I have no idea if it's possible, right? But it's that risk that I love. It's the fact that it's because we're uncomfortable, because we don't really know, that I feel we're going to innovate. And I think that's really important, because as you start this journey, you'll be like, I have no idea, adaptive control machine, transport machine. It might sound strange, and all the tools we're showing you might sound strange, but it's really that excitement and that desire to play and innovate that creates the cool stuff, right? It's not necessarily a full understanding, a full knowledge of what's going on. And I'm talking to Bureau Happel, which it's quite a prestigious client, so when I say let's do it, there is a bit of fear, but at the end of the day, I believe in the process. I believe that through those tools, we're empowered to create more stuff. So this was initial sketch, obviously still not sure how to do it, but then I looked into a technique called lattice hinge. Lattice hinge is when you start creating little springs in wood. It's a technique available open source on the instructables.com. And I just took it to Grasshopper and started doing those matrices of possibilities. Then I started tiling it. And then at the back, to hold the structure, I was looking with James, the engineer, James Solly, how to remove materials that I didn't need in order to create really efficient structures at the back. So this is the CAD file. That's literally what you need to create these things. So this is a tiling of the same thing, but in 3D. Once you start pushing the wood inside and holding it together, it shapes these really interesting waves in wood. So we put LED lights at the back. It came like a sort of IKEA kit, and then we assembled it in shape. The first version had no openings, and the director of Grapple said, we're going to use it to the other space. There'll be a low ceiling. We need some openings. I did this little study with Andre, my colleague, and we put it on the floor, and we're like, okay, well, what's the best one? And I think you might agree the one on the left is the best one. As in, by best, I mean the most natural looking, the most kind of exciting looking. Now, for me, it's nice to kind of step back as a designer because I don't have all the solutions in my mind. On the contrary, I think best solutions emerge. They are obvious. And so for me, it's very important that when it comes to teamwork, best solutions are often obvious. They can be agreed by just everyone saying that one. And yeah, you might have an odd person, a rebel, a French guy, but usually it's fine. So, and the reason I think it's better, it's because it's a fractal. And a fractal means that it self-reproduces itself, given the large scale and the small scale. And I think these are often much more elegant forms in nature. This is sort of stuff we put behind. As engineers, they wanted it to change the temperature of the room, so we just put a phase-changing material at the back. It melts when it's hot, and it releases heat when it cools down in the air. So here's the fractal, waves forming waves, forming waves, forming waves, which created a real depth in the space, when the space was actually quite small. So these are the modules. Being quite traumatized by sending 200 different modules to the machine. With the previous project, we just did 3 panel types. And then by just kind of tapering the edge, it was enough to define a certain curvature. So please don't do 200 files. Do a few and multiply them in order to understand the possibilities. That would be plenty. It's not because a machine can do any shape that you want it to do any shape or that you have the time to do so. These are my students at Westminste. I really like them. They're in a similar idea of, they're broke basically as students. And so one thing with parametric design, it allows you to maximize inexpensive materials. So it allows you to take pieces of MDF to shape them into things that are incredible, and that's because of the kind of intelligence of what you're understanding with the material, right? So here is a reciprocal structure. You have different kind of geometries I want to show you, but these are literally just sticks, right? And it's the way they're organized, it's the way they bend towards something that makes them interesting. Yeah? These are really, really simple little notching things, but this can hold an entire person, whereas this is just cardboard. And so through understanding geometry, they're called space-filling curves and so on, it allowed us to understand how to maximize inexpensive materials. So money should not be an excuse for creativity because you can take very cheap materials. This is Burning Man, and I don't know, anyone went there in the audience or anyone heard of it? Yeah. Okay, good, a little bit, okay. So, it might sound like a cult, it might be actually. These are the 10 rules that we learned there. Google sends their employee there, Facebook as well. You have people like Elon Musk going there, and they all build little cars and they all make something when they go there. The reason being is that everyone is the performer. So there's no band playing or so on. You are the performer, so you bring something with you. I bring my students. And then we build structures that are very cheap and that are very easy to assemble. This is a reciprocal structure made from a very simple little star-shaped component that is being arrayed and that lifts and stays in shape. So we ask our students to speculate what they can become and play with models at 1 to 5 and eventually at 1 to 1, speculating on what sort of architecture this could create. Yes, crazy. But I don't think someone could just draw that. You'd have to let it emerge from your knowledge of materials and so on. So these are some of the examples of the things we built. This is a recursive, very famous pattern called a coach pattern. We built it out of scaffolding, first with pasta, then with MDF, and then it just kind of was delivered on site. IKEA kit again. One thing that's interesting with fabrication is that you end up creating the entire process. So you end up with models that you can assemble on site with people that are not architects necessarily. So we bring lawyers, bankers, people that just are so tired of their job and they just want to experiment with their hands. But by doing so, we are showing people that they can do things. And I think the spirit of what you call making is to allow people to know they can do their products. They don't have to just buy them. They can be part of that making process. So that's the latest one we built last summer. It's called Tangential Dream. I got tired of digital fabrication altogether, at least that time, and thought maybe we can just use off-the-shelf materials to just kind of create a really interesting geometry. So this is called a tangent. So we're going back to the central column. We didn't actually ended up using a central column, so it's interesting to see that. These steps are defining the slope of a curve. The slope of a curve is called a tangent. And it's the very first thing I'll teach probably tomorrow, which is pure vector geometry. And then actually this came from a Grasshopper class, and then I thought it was interesting, and I submitted it to Burning Man, got the grant. And so by changing the angles of the curves that the tangent sits on, it creates these really interesting sweeping geometry. They're all straight lines, there's no curves, and most of it is symmetrical and repeatable, which means that project was very cheap. In fact, in terms of wood, it's 9 meters high. The wood costed only $3,000, which is pretty cheap. It was really bad wood, but it worked. So the only thing that changes here is this. This is a little spacer, and the rest is all standard off-the-shelf. And now when I say off-the-shelf, you can go and buy it in places that sell wood. And so that means you can design based on the things you buy and that you can get for cheap, as opposed to generate a big puzzle that you need to assemble, and the laser might get it wrong and so on. The only thing we had here is a spreadsheet. We just engraved it in wood because it made sense. And then we had a circular saw, and then we just tack, right? It's actually quite easy. No robot needed here. Might be better with a robot though. But here we go. And then it was symmetrical, so all we had to do is put it up. The spacer would tell us the rotation of that curve, which was based on a sine curve. It's slightly more curvy at the top. And so people would climb it, they would write their dreams on the tangents, which is why it's called tangential dreams. The people writing their dreams also helped fund the projects. So it was a very exciting piece, a ladder, a very mysterious ladder that people would write things on. And notice how the light got caught inside those little tangents, which is, again, the idea of scattering the light. And then we burned it because as disassembling it, bringing it back, would actually be more consuming in terms of pollution. So the University of Westminste is pretty happy with us. This is their new campus that we're actually now going to design in Marylebone Road. So the idea of scattering light came to a facade here, which is a kind of light scooping component. So we just got planning application for that. So hopefully it's going to go ahead. And this is a new kind of project. Basically, that whole journey led me to think that, like Johannes, it doesn't scale digital fabrication. It's very hard to scale it. And therefore, we need to rethink the tools. And so this is called a cable robot. It's the idea that instead of having a robotic arm, you'd have straight away the length that you need to achieve connected to winches, which then the winches would be connected to your grasshopper model. And so that means you could assemble things and use this tool as a robot that is very, very cheap, because all it does require is cables and motors, and therefore anyone could build it. And so I'm quite excited at the idea of a robot that anyone can build and that can scale and span hundreds and hundreds of meters. And so that's the latest thing that we're developing in the office. And hopefully this is installed on the 21st of September. I'm scared. Again, you know, the kind of venture, we have no idea if it's even possible or, you know, but yeah, you'll hear more about this as we go. So yeah, so thank you very much. So we'll have a first class this afternoon after an introduction to the robot by Johannes. Yeah.
Thank you, Arco. Any question, guys? Concerns? Are you afraid? Are you still want to be here?
I'm going to constantly ask that question over the next 2 days. I'm having a lot of fun. I haven't seen Arthur in, what, 7, 8 years?
Yeah.
10 years, probably. So that's still the same. I'm getting older.
Any questions to what crazy stuff he's doing? Please.
I can notice that you use a lot of material,
Yeah.
and I have had various questions about your project. What is the most strange or uncommon material that you use?
The most common material.
Uncommon.
Uncommon material.
Or the most recommended?
Chocolate.
Oh yeah, I didn't show that. It's true. I think the food project, I didn't really show the food project, but we 3D printed a whole meal. I think that was very uncommon, and I'm quite interested in it, because you know there is this whole molecular gastronomy movement. So I think the project you showed is another level. It's like more like architectural gastronomy. So knowing the molecular level, so if you can actually model, you know, waffles that are 3-dimensional, and then pour chocolate, and then, you know, then pour another material that you don't expect. I think it'd be very exciting to try out, yeah, kind of food materials, because then you can eat them and feel the architecture.
So probably you can print yourself out of an apple. You can print your face out of an apple or a banana.
For example, that would be a use. It's true. And we get all kinds of requests.
Like if we go back to her question regarding wood or stone or whatever. I don't know.
I think it gets sometimes harder with certain materials. I think stone, I'm very impressed by the project, because I would not even start a project in stone. Maybe I would, but I'd be scared. You know, wood is the obvious, easy material that is just great. You know, whether it comes off the shelf or by sheet. There are materials that are so cheap, you know, polycarbonate, and it's incredible how cheap it is, you know, and sometimes I wonder, because it's plastic, so people have to dig the oil and do some kind of process, and yet it's cheaper than wood. I guess because wood grows over a long time.
For years.
Yeah, but, and what I'm very interested in is now, you know, things like bioplastic. You know, the printing project I showed you, it's made from cornstarch, vinegar, and glycerin. It's called PLA. And so if you can do PLA extrusion, why don't you do PLA sheets? Why is there no PLA sheets? I wonder if plastic could be that, biodegradable, and if it could be much easier to then recycle, and then you can reprint, you know, you crush it, you reprint. All these things are very exciting. You know, we just got a very, very large printer now, 4 meters. And you put pellets, so small pieces, bowls of plastic inside. And so that means you could crush your plastic, put it back in. So the idea of wasting plastic and the oceans full of plastic, I think that's crazy stupid, because now you can do plastic from things you can buy in the supermarket. And so I don't know why it's still a problem, plastic. And you know, I think it's for you guys to kind of change that. You know, pollution is a weird concept when you know the materials now. Yeah.
Thank you.
Yeah.
I was wondering about the lattice that
Yeah.
you showed, about the wood. The question is, do you calculate the final shape, or is it that you calculate how you dig the holes and then you find the final shape while bending it by hand or something like that? How does it work?
That's really interesting as a question. A bit of both. So to simulate how it will bend, it's very, very hard because there's so many hinges. So you can either like reduce them into little triangles so that your hinge is really not a high-res hinge, but you can kind of put little triangles as hinge forces, and then you kind of assign a constant pressure everywhere. But what I noticed is in the computer, I never get the same result as the empirical physical test. So whatever we did in the computer would be informed by the physical experiment. So the physical experiment would then inform that hinge force, or would inform the deflection values or the kind of resistance values and so on, either on Kangaroo or Caramba. Caramba is really good at doing deflection. In this case, we're doing a point force, so we can just kind of push them in and see how it deflects, either with the hinge force or the deflection. And I worked with Rapol on this, and we kind of did so many digital simulation. It's never as accurate as the physical thing. So really, it was really back and forth from the two. Impossible to predict purely on the computer, which I find really interesting.
There's a kind of beauty in that unexpected shape that is going to
Yeah.
What's the name exactly you use? Like
Lattice hinge?
Lattice hinge.
Lattice hinge, yeah. Lattice hinge, the person who puts it on, someone put it online as a kind of file. It is called Aaron Porterfield, and it's on theinstructables.com. Theinstructables.com is a website in which people put their recipes for design and so on, you know, and you can download the steps. So it's physical hacking, really. And this guy put that on, and then I downloaded it, then I played with it, then I kind of sent it back to him, then we became friends. Then he came to Burning Man, and now he's going back to Burning Man. So it's really interesting, that community. Yeah. So it's not just digital open source, it's also physical things, which would be really interesting in architecture, really, because we reinvent everything per project, which is a bit crazy, right? Like, if we were to share our discovery and put them online, then other people could kind of experiment based on that, share again. I'm surprised there's not more platforms to share architectural modules and discoveries. Of course, there's BIM, but it's very commercially driven. I wonder if there would be an equivalent. That would be another great website, like the End Effectors one. Yeah.
Because all of these experiments that people like you guys do, it's all kind of open up to research and collaboration and sharing the knowledge to be able to get more talent involved and
Yeah.
more communities. You know? That's all very important to push the research. Lunch.